In a lot of systems, feedback loops or mobile control systems are better. You can think about it as to prevent you want to have mobile things, signs up, or things to prevent traffic accidents, or in case mobile tech loops to prevent if you have a plane flying, you might want to have mobile checks to make sure that it's staying balanced and level, so it doesn't suddenly jerk one side to another side. So you have your mobile things on the wings to control it. Controls on the different tips or surfaces. You might have mobile controls in your house to regulate the temperature, like big controls, little controls, and all these different things. With internet traffic, anything that you need mobile control, then it might be useful to have mobile controls in case one of them messes up, or for fast responses, because they can be a lot faster because it's more local, or the computations can be more easy than sending it all to a central computer that does better, faster computation. However, I want to point some things to go in the design of that. One is that it's not good to usually have just one big on-off switch with a center. Either you have to take that big on-off switch and make it into a continuous thing, like a dimmer that has an on-off both in between settings, or you have to make it so it has one switch cannot fully turn on off the system. One switch can only turn on half the system or something for fail-safe, and have many small switches. The reason for that is, imagine you have a system that you want to go to a maximum of 3. More than that is over 1. Well, if the data from if the controls which I put here, if the controls that are small first go off, then the bigger control goes off, it's a lot easier to go over it. Have a number 5 or 2. Then it might undercorrect to see that it's over and go to 2 or 3. So it's now if that switch was 1, if all the switches add up to a maximum of 3, the maximum value, it's never going to go above 3. Now, why would that happen in the system? Well, it could be because there's time delays, so not all the sensors are looking at the other sensors at the same amount. It could be that there's environmental feedback. So cases of environmental feedback would be like, for example, if I raise your body temperature if I raise your body temperature in your finger and part of your body's still your body's not going to suddenly get warmer throughout your body, because some cold blood is going to go through there, and that cold blood that's going through your body will not respond as fast, so I can keep pumping in heat quickly, but suddenly that hot blood that was pumped away from that section is going to come back, and your whole body's going to be a lot hotter than it was before because of that time delay. Or one that could happen is that I put in something, I let more traffic through in 2 places, and suddenly all the traffic coalesces and there's a giant traffic jam. Trying to think about one that's more environmental, adding up together, but interaction environment, where you have loops, positive feedback loops you could have. Maybe if I heat up your body starts getting more information, which can cause a positive feedback loop actually. Heat can cause inflammation, which makes more heat. But all these ones. Another thing that would help is not to look at the exact not look at the exact numbers, but to look at the derivative or something along the derivative. Now, the exact numbers are done here. So let's say this is a curve. The derivative at a point in the curve, which I'm going to call here, is the rate of change. So that means that the switch is turning on more and more fast if the rate of change is bigger, or if the rate of change is, or if the actual not only is it turning on and off, so if it's slowly changing, you don't pump up the system very fast up. Or, yeah, this will give a lot of benefits because you can get a system, you can encounter with this little thing of adjusting for it, you can start adjusting for a wide range of unintended consequences of environment with feedback loops that you might not think. You don't know if a person might have information. You don't know that if opening up one lane will cause everyone suddenly to switch that one lane, or that feedback loop, or you don't know if it's going to cause big behavioral patterns or changes in flight. Maybe you start turning, and suddenly there's a huge, massive change with the aerodynamic because you're turning into a cloud or something. This response will let you quickly correct it when you need it and not, and wait for the environment to catch up or the other sensors to catch up. The other sensors start acting slow or takes a while for the data. This gets ready, and you can actually learn about the system more. So if you combine this with an AI or learning algorithm, this idea of doing it with the rate, because you were waiting for the rate, because the rate adjusts, we can wait to see more easily distinguish it from the environmental background and more easily cause an algorithm to learn how the environment is affecting it, making it even better able to respond to the environment. The other cool thing is, it's very easy to make it, with this design, much more modular if you look at the rate. So if I have this, without looking at the rates, if I just add control, this is the smaller controls, and I'm making 3, this is the bigger controls. This is the bigger, then there's a bigger control over here. Here, that's connected, and that's connected, these two are connected to even bigger control. Over here, every time I add a layer, each layer depends more on the previous layer, and doesn't do more computation, just either adds or subtracts. But if I have it based on the derivative, this each layer above it actually adjusts the rate of change of the layer below it. So this one acts to change stuff. So the bottom layer acts to change stuff a little bit, but really fast. The top layer more fine-tunes it for longer running things and patterns, but also bigger things. The layer above it fine-tunes it even more, and each acts as a more hierarchical thing. Because this is not looking at just the rate of change. This is one above it is looking at the rate of change of the rate of change too, and it can do much more fancy curves and patterns, much better. Because what happens with the old one is I'm just fitting almost data. Another way to think about it is you just fitting points to the data. Next one you're fitting kind of lines. And this one you're kind of fitting parabolas in the third order, and so on and so on. You get higher order fitting. The other cool thing, and then also that even makes learning better. The other cool thing is you have to worry about how each of these nodes are connected less. So because they can self-adjust, meaning you don't have to worry that control parameter 1 is connected to control parameter 2 or 3, or that they're connected like a triangle, or they're just connected like a tree, all these different controls, and the exact amounts, because it'd be self-adjusting, regulating, which means it's easier just to add on stuff to the system. I hope you found this interesting and informative. And the reason why I'm saying all this might be for the future, and if you ever go into designing systems, and if you ever wonder why the derivative is so important and rate of change. If you want to learn more about this and fine-tuning, please like and subscribe. It really helps the channel out. Thank you very much. Goodbye.